Yeah, hello everyone. I'll be going through how to implement the systolic array you have developed in the previous sessions on a sync SoC on the FPGA and connecting it with the sync processor. So this is the structure of the systolic array that has been introduced in the previous session, and here it has been shown to integrate with the Ibex SoC uh, through the AXI connections. But similarly, we can also implement this on a sync SoC instead. So sync is so it's a the system on chip. It has the FPGA part, the programmable logic, and also a processing system. So it has some ARM processing cores. So there are many. So these are all Xilinx boards, and like there are many versions of them. And this diagram is for the Sync 7000. And there is also a Sync Ultra Scale, which has it's a more powerful SoC. Like it has larger programmable logic and also like more cores to the processor. So the process that I'm going to show it can be implemented in any uh, SoC based on like this sync. I will try to make it as general as possible. So because if you have an SoC development board, then you can try implementing it yourself. Uh, so I have cloned the repository. Yeah, I have cloned the repository, and so I will be doing the implementation on a, um, a Kriya KV260 board. That's just what I have with me. And like the repo has some automated flow to create the project and like do the all the building things automatically for these three boards, like the pink and these two are Sync Ultra Scale boards. So if you have these boards, you might be able to run this flow automatically. I will first show how to do that. And if it's not like it could be possible to edit this file to fit other boards, but if you are a beginner, it might be easier to use the GUI. So this process, like to implement something on the Sync SoC, you have to use Vivado because it's a Xilinx board. And so the TCL file, like the TCL files shown here, they are sort of the purpose of them are like instead of doing every step on a GUI, you can like these are all the steps that you might run on a GUI, but it's all automated. So you can do it in like one step. That's the purpose of TCL file. So I will first quickly show how to run that automated flow, and then I will go through the GUI steps so that uh, like that might be easier to follow if you are a newcomer to uh, like implementing stuff for an SoC. So I am at the inside the repo now in the terminal, and these because the flow has been built using a make file, to make it work, you have to use a zip bash shell if you are using Windows. If you are using Linux, it will be fine. And uh, so I will just, so this readme also has the steps, and you need to have the prerequisites of, like, this is for very little, so you might have installed these things before, like you have to have make uh, and git bash if you are using Windows. And these are the steps for implementing on the FPGA using that automated flow that I mentioned. So we can use this command make Vivado. So I have made a custom TCL file for my board. So I'm going to use that one. Like, otherwise, like, you can use the name of the file, whichever board that you are using. So, so this is just a problem with my laptop, the Python installation. So this make file does two things here. Like, first it's uh setting some configurations. So like here they have defined, so this is a matrix multiplier. So here, like, at the top level, we have defined the dimensions of that, and the data types, and the address widths, and the axi bus widths, like all of the things that we need for defining the, like, various parameters of the project has been defined here. So from it, like, using these variables, it's creating some config files. So config files are used in various places. So the advantage of doing it this way is, like, you don't need to define the same thing in multiple places. So if you need to change the data type of one matrix, for example, you don't you don't have to go to multiple files and then forget to change something. So that won't happen if you, like, generate it all and using a same, like, single source. So there is a config.svh file. This is used included in the Verilog code, and there is a config.tcl file. This is used for the TCL automated flow. These are referenced by that. And the config.h is used in the firmware when we make the like, write the C code to drive this systolic array. So you can see that those variables are used in both places. Uh, and I will show where, like, these things are used when we are running the flow using the GUI. Uh, and the next thing that's done by this is to download the board store, because like, that will have sort of the specifications of the uh, various ZYNQ SoC boards that you might have, and those are not automatically installed in Vivado sometimes. And then it's trying to run the, like, so Vivado, like, normally you might have opened it with the GUI, but you can run it using the command line also. So that's what it is doing here. And it's opening as the batch mode, and then you can give a TCL file. So it's telling to open Vivado and run all of these commands. So here, like actually it has failed here because like I think this is something to do with Windows. Uh, because I couldn't get it to work at once. So like when you run this thing first in Windows, you might get an error that Vivado is not found. So if that happens, that means like it's not, the command is not in the path. And in Vivado, there is like at the Vivado install location, there will be a file called like this is inside the your Vivado versions. There should be file called settings64.sh. So this is a bash script that will sort of initialize some environment variables, and you can run source and this file name. Uh, so those variables will be initialized, and now you can see that like I will open Vivado in TCL mode, means it's a yeah it's some issue there, but anyway, the Vivado command is working now, so you won't get this error. Now I will run. So if you are using Linux, you won't have this issue. Like usually when you install Vivado, uh, the Vivado command will be added to the path, and if not, you can add it to the path yourself and or source this at the beginning. So for some reason, if I source this at the beginning in Windows, it doesn't, the make file doesn't work. So that's why I did it this way. So now if I run this, so now Vivado batch mode is running. So you can see like it's like you can go here, and if I open this file, like create project is now running. So all of these commands will run, and at the end, it will like automatically create the project, add the modules, and run the synthesis and implementation. It will do everything automatically. So I am going to terminate this because it will take a while, and uh, I want to show it in the GUI also. Uh, for that, I will open a new shell because we need to even see due to the way this project is configured, like we have to run that config make file before even if we use the GUI, because it will create those config files that we will need to use. So here like same error, but the config files have been created, so we can refer to them like because the RTL files will expect this file, and the C code will need this file, so we need to make that anyway. So now I will go to Vivado, like in the GUI, and I will make a project inside the run work directory. So you can see that the previous project that I ran, like when I ran the automated flow, it has created this is the project, Vivado project that it has created. I stopped it midway. so it's not a complete run. Uh, so so then for the project sources, we will be adding the RTL directory completely, and also the config.svh file that was generated, and that's in run.work. So I have added these files. And here in this project, there is no need for constraints because this is a sync project, and so the FPGA like PL will be getting its clock signal from the sync like processor. So it processor can like the PS can control which PL clock frequency that we can give. So since we can configure it there, we don't need to add a separate constraint for the clock frequency here. And here we need to select the board we are using. So since we downloaded that board store, I think like you should be able to find most of the available sync boards uh, on this like uh, yeah. So this is my board. And yeah, for some boards, like I think if we are using something like the cyber board, those the board files has to be installed in some other way because it's not like made by Xilinx directly. I'm not exactly sure, but that you might have to follow a different procedure to add the board file to Vivado. So the project is created, and uh, so it will show a syntax error file, but you can ignore it. It's not in use now. And you can like this is the current top module of the systolic array. So I will make it the top module for now. Later we will be changing that. And yeah, then you can create block design. So the block design is like so previously you will have created the Verilog files or system Verilog files like in that. So this is example, for example, the systolic array top module, and so you can see that it has initialized various modules and connected them uh, using the signals defined in the file. So, but this might like when there are so many signals, especially when we are working with AXI, so this might be a bit tedious. So in Vivado, like if you are using Vivado, there is a so the block designs are sort of easier way to do those connections. So it will sort of bundle us a whole port together. Like if there are port uh, 10 signals you need to connect between two modules, like it can bundle those signals together so that it's much easier to connect. So that's sort of the purpose of the block design. Uh, and here I'm going to first add the ZYNQ ultra scale SoC. So this is the sort of representation of the processing system. My board has a ZYNQ ultra scale. That's why like I used it. If you are using a ZYNQ 7000 or pink board, the you will see it as, you see the ZYNQ 7, you will get this one. Anyway, when you search the uh, IP, you will see the relevant processing system for the board you have selected. So this is sort of the IP representing the ZYNQ ultra-scale processing system. And we first need to you can use this run block automation to do most of the things actually when making a more simple block design. So first we can apply the board preset. That means like the default settings for this PS. And then so in our SoC, so we need to, like, if you look at the axis connections from the uh, PS to the systolic array, so there is one axillary connection, like where the processor is sort of giving the instructions, not instructions, like configurations to the DMA controller to what to do, what to fetch, that kind of thing. And there are four axis connections, like from the DMAs, three for the input matrices and one for the output matrix. So this will be these are controlled by the DMA controller. So it will be sort of requesting the processor to let it access certain parts of the memory to fetch it back into the FPGA. So we need one master port. So the processor is controlling the systolic array, and four slave axis ports where the systolic array DMA control is controlling the processor. And those can be added. So you have to go to PSPL configuration. So that means like the interfaces that will connect the PS and the PL together. Those are those axis interfaces in the middle. And master interface. So currently two of them are ticked. The way like the addresses are configured, you have to use HPM1 in this project. And for slave interfaces, you can use the first four of this, since we need four of them. This high performance, like if HPC ports are high performance coherent ports. So it's not that relevant to this project, since we are like dealing with that in the firmware, but like the use of this is if you are so we are using these to access the main memory of the SoC, right? But the processor is also accessing the main memory, and they are not synced with each other. So since there are caches and everything like on the processor, what the something that's in the memory might be not be seen the same way by the processor and the PL at the same time. So then there's a coherence issue, and these SPC ports are designed to like avoid that. But in this project, the firmware is anyway flushing the cache, so I will explain that later. So it doesn't matter if we are using HPC or HP here. Anyway, there is only two of them. And also we have to change the data width of each of these into 32-bit. So now you can see like it has updated to like so one master port and the four slave ports. Then we have to change some configurations based on this config.tcl that was generated. So it will have the clock frequency that we need to set. And also like so the previously I showed the TCL file flow. So you can see that in this TCL console, everything that we did using the GUI, like it appears as a TCL command. So if you look at this one, uh, so it's the, and if you look at this, like these are the, like up to here, this part is the same command. So if you are new to like automating using the TCL scripts, the easiest way to start is to like do the steps on the GUI and then use those commands. Uh, like copy them all to a TCL file. And you can do the other way also. Like you don't have to run it separately using a make file or anything. You can even run like you can type a TCL command here and it will run it and you can see it working on the GUI. So then, yeah, there is the clock frequency. You can check what is the, so that's the out clock frequency that's provided from the sync SoC to the TL, the FPGA part. So in clock configurations, output clocks and low power domain clocks. Here we have the PL clocks. So you can see it's 100 megahertz, both of, if you need, you don't really need both of them, it's one is enough. And if you need to change this to something else, you can change here. Here, since the config is set to 100, we'll be using 100. And so then, so you can, so the, to the block design, you can add any, like there are many IPs that are sort of developed by Xilinx. So they are sort of proprietary IPs uh, that you can use in add them to block design. So you can search them here. So I think in the last session you used a open source DMA IP. Like if you are just using Vivado and Xilinx, there is a DMA IP here also if you need to use that. And also, apart from that, you can create your own IPs, which is a bit complex process. But if your code is written in Verilog, you can also like directly add Verilog modules to this block design as well. So we are going to do that now for the top module. So right click, add module, and select the top module. So there will be error here because like this is sort of a quirk, like difference between the Vivado like TCL Flow and the GUI. It's saying it can't find the config.svh file. You might not get it, so I don't know. I'm not exactly sure whether this is something to do with my version or what is it, but it didn't, so it didn't happen in the TCL flow. So as far as I know, it's a difference between how the GUI validation and the TCL script validation works. So here, because the problem here is that we have the top axis in this RTL folder and config.svh is in the front folder. So it can't find, like it's expecting to directly find it, but it's not finding. So I am going to put the relative path to config.svh here. So if you are using the like automated flow, you don't need to do this. Now we should be able to add the top module. So here also like you can see that So if you look at top axis, like all of the, like there are lots of wire input output ports, but this has detected and no, not detected, like you have to follow a specific naming scheme. Like it will bundle all the signals that start with this part as one port. So if you expand this, you can see all of everything, all the signals inside it. Same with this. So this makes it like much easier to like see this module at a high level, since like there is not a huge number of signals visible. Uh, then we have to connect these two. So this process, like you can use the run connection automation tool for most of this. So first we will be connecting. So, but when you are using it, you have to be careful on what it is trying to connect to what. So first I'm going to connect the axis slave of this one to the axis master of the sync uh, SoC. So I'm selecting the S axis here. So the master interface, it has we have to always check whether this is correct, connecting to the correct thing. So HP, it's connecting to HPM1 here. That's correct. Uh, and then so now it will automatically add some components. So the processing system reset is like this is uh, used to this is a module that's used to sync the reset with the clock, PL clock, uh, before giving it to the various modules in the PL. And the Axis Smart Connect is like a Axis Interconnect bus that's that can like flexibly connect between master and slave Axis interface. So like yeah, uh, and then we have to connect these four slave. I will bring this to here. Then we have to connect these four slave these side master interfaces to the sync SoC slave interfaces. So you can connect this directly also, since they have the same data widths. But if you do run connection automation, like you can do this, like there are no resource conditions, you don't have to worry about this. But if you do it with run connection automation, so I'm going to do the first top one first, and I'm going to connect it to uh, the MM2S0. Yeah, here we can select which one to connect to. Uh, and if we do it this way, it will add another smart connect. So the reason for this is like it wants to make it more flexible. So example, if you have different, so here the data width of the two ports are the same, but if you have different data widths, like that will be handled by the smart connect IP. Uh, so like there are some advantages like that, which is why Vivado is automatically using that. Uh, but if you like in this case, you can just connect it this way also, since the ports are all like the ports are matching between these two mostly. Like there are extra signals here that are not used here. That is another thing that will be handled by the smart card. Uh, but if the ports are when the ports are matching, you can do this. Otherwise, you can do like keep using run connection automation also. It will show which also like if you don't use that, you have to manually connect the all the like clocks corresponding to each of the ports to the clock main clock TL clock signal. So I'm going to do the manual connection here. If you do connection automation, like it will automatically connect these clocks as well. Here you can do it both ways. And yeah, now you can see like since all the important ports are connected, like that run connection automation thing has disappeared. So now you can validate this. I will you like you can use the regenerate layout to like have a nicer layout for this like make it more clean. And then you have to do validate block design. So this will do two things. It will check whether all of the connections are valid. So if there is data with mismatches or something like that, it will warn you. And it will also do the address assignment. So since like all of these axis connections need to have address segments from which you can communicate between them. So this will automatically assign the address segments also. So validation is successful. And then we can go to the address editor tab. So these are the addresses it assigned. And also like there is this QSP, I think. I think like in the other flow, it has disabled the QSP. Peripheral. Yeah, now we don't have that. So these are all the like address assignments of each of the five axis connections that we have. The first four is for these four interfaces. So it's from the perspective of the top module. And like since like they are not having any other, like it's only connecting to one thing. So it's just starting from zero for all of this. The important one is the other one. So the ZYNQ SoC has many peripherals that it needs to connect. So it has different address ranges allocated for each of those components. So it's only like a specific range that can be assigned to the this axis axis master interface. So this one. So that one you can see here. And according to our like config file that was created, so uh, so because we are going to refer this config base address in the when we are writing the firmware, so we have to modify the addresses according to this. So we have to set the config base address like it's currently. Yeah. So I have changed the address of this so remember like it's like the it should be from this like from the perspective of the PS, and like that PS is the master, so that's the one where we need to change because we are in the firmware we are controlling the systolic array through this connection. And like this one shows like you can see that the address we have set is like shown here like B and 7 zeros. Uh, that's because like since there are many different uh, interfaces that the sync SoC connects to, it has like Vivado has like it has determined like these are the address ranges that you should use for this particular port. You can't just use any address because it might overlap with something else. It has allocated space. Uh, so that's why I previously got an error when I changed to this with 4G because it has said that it has to be 256 megabytes. And yeah, then we can validate again if we want, just to make sure the address is correct. And then save the block design. So after that, uh, so now this should be the top module, not just this top axis, because this is what we need to implement, including these smart connects and everything. So to this, like we can't directly make this a top module. We have to make a HDL wrapper. So it will make a sort of this block design with a Verilog file. Yeah, now we can see it as design one wrapper, and inside that we have the block design. So now we can make this wrapper as the top module. Uh, then we can run synthesis and implementation and generate the bit stream. So you had to do all of that. So I'm directly going to do generate bit stream. Then it will like start synthesis and implementation and all of that. So this will it's going to take some time. So I have another project that I made earlier where write bit stream is complete. So if you want to check the uh, resource utilization or something, you can do it from here. So in the automated TCL flow, it has another part to generate the reports, and it will appear in reports here. So when you are using the GUI, you can just open the, yeah, this is taking some time, so I will cancel this. And I will also cancel this. Things like I'm not going to. I will continue with the other project that is already synthesized. So the next thing after write bitstream is complete is to is to export the hardware. So here, export hardware. So the purpose of this is like we have synthesized this for to and implemented it like for the FPGA design now. But in this case, like rather than directly uploading it to the FPGA, we are going to uh, write firmware using Vitis and then run the like whole thing from there. So Vitis will need to know like Vitis is the sort of software platform. So this is sort of the connecting file between the hardware and software. So the hardware, this hardware platform file, we need to do include bitstream. So because we are not programming the FPGA from the from Vivado, we are going to do that from Vitis also. So the bitstream for programming should be included in the file. And apart from that, it will also include things like the address map that we I showed before. So it will show which addresses will connect to which components and which IP blocks we have used. So it's not relevant here, but like if you use a DMA, Silence DMA IP, it will have its own drivers that you can use in your firmware. So it will show that these IPs are included, so Vitis can include those libraries. Uh, and like all the settings that we have selected on the PS, that since like this PS component, like this is only sort of a representation. It's not implemented in the FPGA. So because there is already a processor in our SoC board. Uh, and the settings we have set here, like it will be used to configure the PS to, and it will show to enable these ports and these ports, things like that. So that's the purpose of the XSA file. I will put a different name here. Uh, so now, so I have opened Vitis now. Uh, And in Vitis, like you have to use, I'm using Vitis Classic here. The Vitis, like new Vitis is sort of a different, it has different interface. The classic one is easier to use. Uh, from here, I'm going to create new application project. So here, like this is how this also shows a diagram of how the Vitis project works. It has multiple parts. So here we have to give the XSA, and using the XSA, it will create something called the platform project. So the platform project will have all the details of the hardware that we have sort of brought in from the XSA file, and we can connect that to a system project. So system project is like sort of it's the connection between the program we are running and the platform. And within the system project, we have the app or the application project. So this one actually contains all the code that we are running. It will all the C files. And if you are so some C processors have multiple cores. So if you are having a multi-core processor, you can have multiple application projects for each core, things like that. That's why there are two things called system project and application project. And so here we have to create new hardware platform from XSA. And yeah, I will. select selected the XSA file that I created. So we can give a name to the project. We can keep default settings here. And you have to use the hello world template. So we will be replacing the C code of the hello world, but like there are some additional files uh, that are automatically added to this project to support things like printing and some other things. So until this is creating, I will briefly explain the C code. So I think some parts of the firmware was explained in the yesterday's session. So I will just go over this briefly. So here there is this structure called memory st that is defined in config.h, and like this contains the four matrices, like three input matrices and the put matrix with the like defined uh, dimensions and data types. So here we have initialized a variable with that structure. So this is allocating memory for the matrices that we need to use. Then this is a pointer for the config base address. So that is the one that we set in the address editor before. So this is the base address we are using to communicate with the taxi light interface, to communicate with the DMA control. Yeah, so uh, here this is the ignore this. These are the previous test projects, some test projects I made. And this is the platform project that we made. So this will have all the details of the hardware. And this is the system project, and this is the application project. And inside the application project, we have the source file. And this is just a hello world. I will replace it with this silence example. And then, so you can see that it gives include errors for these three files. And that's because they are in different folders. So to resolve that, you can go to C++ build settings and directories, and then include. So the config.h file is in run/work. So this is different. Uh, and then the next one is firmware.h is is in the C folder. And then this FBFW wrap is in the file bridge folder. So I have added all of these. Now those included as disappear. And we can build the, so when building, you have to build the system project because then it will build the like the platform and the application project, it will build the whole thing. If we just click on this and building, won't build the platform. So this will again take some time, so I will continue explaining the code. And first thing this is like randomize inputs. Like this is just setting some random values to each of these input matrices. And then it's doing 100 runs for the systolic array. And first it does flush cache. So I mentioned this about when talking about the high performance coherent port. So because one of those ports we used here, like one of this is normal axis HP port. So it doesn't have coherence. So in this case, both the FPGA, like our DMA controller and the PS is both trying to modify the memory. Because like when have done the systolic array computation, the output will be saved to the memory. But since the PS will be using a cache, so it might not have the updated value of that thing that was modified. So if that happens, like you might see the output as 0, even though it has been computed, because the value in the cache is outdated. So to ensure that doesn't happen, we are doing this cache flush range. So it will flush everything in the cache in the address ranges that we have given, so that uh, the processor is forced to fetch directly from main memory, and it won't have any uh, mismatch issues with the one that is visible to the PL. Then this run command. I think this was discussed in yesterday's session. This is setting the configurations at the register like addresses corresponding to the DMA. So it's setting these addresses of each of the input matrices and what is their size. And also setting the location where it needs to save the output after computation and that one size. And finally, it's giving the start signal indicating to start the computation. And then it will wait until the done signal is given. After that, uh, there is check output. Check output will just do the same thing in software and compare it with the FPGA systolic array output. So now it's built. So I will turn on my board. So we have to connect to the correct serial port. So if you don't know it, like you can find it in the device manager. So under comports, it will show normally these serial ports are what corresponds to the FPGA. If that's the only thing you have connected. So my one is, I have found it before, it's COM9. So most board, this board has been it's configured to try to boot Linux at the startup. So I have to run a small command to change that. This is not needed for most boards. like if we are using a Saibo or Z-board or Pink, that kind of thing, this might is not needed. And now I have connected to the serial terminal and the board is turned on. Now to run this, I have to like select the application project and run as launch hardware, single application debug. So then it will first program the FPGA using the bit stream that we have included in the XS set, and then it will run the like initialize the processor and run the program on the processor. Yeah, I think something went wrong here. Like yeah, seems like something went wrong with the project that I have created now. So I am going to stop this and I will show it with the project I have created before. Like this is basically the same thing. I think the old project I have created might have had some issue that prevented it from running. So like it doesn't print done, so it has it's hanging somewhere. That's the problem. So I have this old project that I have made. So it's the basically same thing. I have replaced hello world and I have compiled it. I will compile it again. Yeah, it's compiled. So it's still there. Yeah, so this one ran correctly. I think like I didn't synthesize this now. I used the old synthesis result. I think something has gone wrong with that one. Might be something outdated. But like if you follow these steps correctly, it should run as shown here. So we have run 100 runs and it says total time taken is this much. And all the outputs have matched. So the systolic array output and the software computed outputs are the same. That means like there is no, we have correctly sent the data and correctly captured the data. And the systolic array works properly. So that's how you can implement this on the FPGA on a SoC development board. And I think from the instructions I gave, you can follow it with your own board. So I showed it for ZYNQ Ultra scale, but you can do it in the exact same steps for ZYNQ normal ZYNQ 7. So I will just show like just you can add this only difference will be the processing system and you can do run block automation uh instead of using that direct connection to make sure like all the there are no port mismatches and then it will be you can run it with uh, most boards you have I hope. So yeah, though that's the process of running on the FPGA. And yeah, I will hand over back to Abba for the Ibex integration part.
Anuki, so the make Vivado command that basically is already working, right? from in building the, is it?
Yeah, so I'm like it's configured for like these specific boards, right? You have to change some
Yes.
things to make it work for others. That's why I went
Okay.
through the
Can you
GUI
show
flow.
them like how you created the KV260 tickle? Like,
Okay.
I mean,
So
what are the things that you had to change? Like, I mean, can you show the structure of the other boards and how you map that to the
yeah, sure.
KV260? So that way
Yeah,
they
sure.
can do, yeah, Vertex Ultra or something, whatever.
Yeah. So since the my board also has a sync ultra scale, I just took this one and so the only thing I had to change for mine was the part and board name. So uh, there is an extra thing for my board that I had to know, like there we have to define a connector because this that was a system on module, a bit different one. So part name and board name I had to check from the I think in Vivado you can do some command like get board parts, and this will have sort of all the options of the boards that you have installed, and you can use the correct board part from here. And also, I think if you like in the GUI, if you create a project, it should like yeah, it also shows the part you have used. And if you set the board, like yeah, these commands are already shown here. So if you are not sure about what is your board, you can try creating project and copy those commands to here. But yeah, if you have a sync 7000, uh, like this part won't work. Like this is a sync ultra scale module. In that case, you should be able to do it with the this T by copying this TCL file and yeah, using this one and just changing the part name here. Uh, yeah, I'm not sure whether there are any quirks of other boards that won't make it not work directly for with these scripts. So you just have to try that. Yeah. Is there anything else?
All right. So yeah, one thing is like yeah, so this for the students, like if you are doing some weird board, like some new board, like where there is not one of these boards, then like I mean, so the one of the easy way of doing that is like if you scroll down, Anuki, if you can scroll down and show the variables at the bottom of the script. Yeah. So the way that we have written this script is that now the rest of the Vivado script, which actually builds everything and connects everything, uses these variables. That is ZYNQ PS. What is the name of the ZYNQ PS? And the IRQ is the name of what this. What is that interrupt pin? And like you have like what you have. What is the name of the clock port? And like the four the slave ports, and then you have like all what different clock ports names and everything, right? So as long as you set these things correctly, then you can use any board you want. So what you can do is like you just create like the ZYNQ PS for like I mean if you have a new board or whatever, then like create a block diagram, create the ZYNQ PS, and set basically this many slave ports, so this many master ports and all that, and then like look at them and write these, change these variable names accordingly. So, and by doing that, and then like you have to put this the ZYNQ set ZYNQ command, right? Like the create ZYNQ processing system and set property for that. So that command also you have to copy and paste from there. And if you do only those two things, then like basically you can make the whole thing work for any different board. So that is sort of the idea. But I mean, you might have some corner cases, but I think those things you can figure out. But like at least like most of the way you can do it by like this. Okay. All right. Great. Okay. So okay. Thank you so much. Okay. For the demo. So
There's a question. I think I did see it before. It's asking if I'm using a Vertex Scale, can I use the same sync processing system? I think Vertex Scale is just the FPGA part. It's just the PL fabric. It doesn't have a PS, so you won't be able to use that. Yeah, that's the only question. Abba, you can take off.
yeah, sure. Excellent. Okay. Right. Thank you so much. So yeah. So like do you have any questions, any other questions about the FPGA flow? So as I kept okay, how do you add open source IP to the block diagram? Yeah, so maybe Anuki, can you like probably try to drag and drop it? So I think like most of these IPs you can just drag and drop them. But I personally recommend you to like not use the block diagram too much because it's a big hassle to reproduce. And I mean, I have written like pickle scripts to avoid this problem, but then there are some issues like what between the Vivado versions and everything, the tickle scripts don't work well, right? So I want to keep the tickle script as minimum as possible in my projects. So which way like so which is why I just create like integrate this open source BMS and everything in Verilog itself. So that way you can pass down parameters easily. So in tickle scripts, it's much harder to pass parameters. You have to take the same parameter, you have to give it to every different thing. So the parameters have to go from Verilog to, and you can't send the parameters from Verilog to tickle very easily. So you have like a bunch of issues like that. So yeah. Otherwise, you can. I think if you really want, you can just drag and drop the IP to Vivado. Okay, and I think like I mean I tried it and it says like it what there was some sort of so the thing is like Vivado block diagram has some problems with in the sense what it has some very specific like reasons on like what the top module should look like. You should not use system verilog. You have to use verilog stuff like that. So because of that, like I mean, you might have some issues when like copying stuff. But yeah, as I said, you can just put everything together in your own Verilog file, and you can like introduce that to block diagram. Okay. Any other questions about FPGA design? So yeah, and as I have been telling repeatedly from the beginning, the reason that we are teaching this, like one of the big reason for this workshop is that you can should be able to take our repo, replace the systolic array with your own accelerator, and you can get it running on different FPGA boards with Ibex and with your firmware, and you should be able to do like a lot of things very easily, right? So that way, like I mean, so you should ask from that perspective like how you can integrate your own module and stuff like that. Yeah, that's a good question. Like, can you share the boot pickle file to change the default pedal enough boot to bare metal? Yeah. So we can probably add that to the repo as well. So yeah, like or else we can put it in Google Drive, right?
Yeah, actually, I don't think that's required for most boards. Like those Kriya boards, I think are the only ones that are configured that way.
Okay.
Yeah, we will add it to the drive.
So any other questions about like I mean putting your own projects like this? Okay. So yeah, one more thing about the GUI flow thing. So when you are building something up newly, so like for example, if you are putting using some of the Xilinx IPs, or if you want to sort of like incrementally like maybe put something together or something, you can use the GUI flow. But then I think like once you like I mean once you like as an experiment you put stuff together and it runs or something, then I highly recommend not doing the GUI at all. So because it's very hard to reproduce the GUI results, right? So just like I mean, we had this problem like right now that like the thing that was running previously was hanging when you build things through GUI. So it will take like a long time in a sense, like several hours to debug why that happened, right? So usually like it might be some port with mismatches. So like I mean, what something was like was an issue or whatever, right? So you have all these problems. So then I highly recommend you to like always try to use the what keep as much stuff as you can in Verilog, right? And use like a very simple like what that means use open source IPs and everything, put everything in Verilog. And then the tickle scripts, you write them to automate the GUI, and that also you keep them as simple as possible, right? So, I mean, previously I used to write several, like, I mean, 100, 200 lines of tickle scripts. So basically create a DMA, configure the DMA with different parameters, and then like create floating point units and use that floating point unit and everything, all that. But then I realized, okay, that's a really bad idea when you go from one version to another version, and then like, so what and Xilinx is not like a very good software environment, right? So keep the tickle script as small as possible and try to do it what like this way, like that we have shown um, in the like README and all. So so having like this, and then so that is very reproducible because you can track the Verilog files, you can track the tickle files. So when you have a lot of stuff in Verilog, you can simulate them also, right? So you can, I taught you about how to use our XC simulation test benches. So you can like basically build your XC VIPs and everything, and that way you can simulate your XC designs. So and by doing all that, you can eliminate most of the problems before you go to FPGA. So our goal is we want to like test as much as possible, and the moment you put it on FPGA, it should work. And if it doesn't work, then it's going to be a big pain, and it's going to take like several, like couple of weeks to fix that problem. And we don't want to do that. And debugging anything in FPGA is hard, right? So yeah, and so the only thing that you need to sort of like still painful from our flow is that the what is SDK stuff, right? That is like you still have to click the buttons. You have to yeah. So you have to basically click the buttons accordingly, import the right files, and we have to do a bunch of things. So I have a few undergrads at UCSD who are currently converting that into article scripts. So it is possible, but then like it was not very reproducible across the different versions and everything. But now in the latest version, 2024 and 2025, Xilinx is introducing a unified IDE or something, and through that, it seems like you can create what reproducible tickle flows and everything for the software side as well, not just the hardware, right? So that way, like we hope to have this end-to-end stuff. That way, like you don't have to like students like you don't have to worry too much about getting the things running because we all want to write our systolic arrays. We want to write our accelerators. We don't want to do all of these other things which are very painful and hard to debug, right? Okay. So could you please okay, right? Any other questions? And if not, we can move to Ibex. Okay, yeah. So let me share my screen. Um, yes, and screen one. Okay, okay, great. So, mm, okay. So now let's look at how you can integrate this into an open source SoC. So this Ibex RISC-V core is one of the like multiple RISC-V processors out there, like RISC-V SoCs out there. So if you search this, it was developed as a part of Pulp platform. So this Pulp is like pretty famous. It's from ETH Zurich in Switzerland. So they are doing like really good computer architecture work, especially building open source hardware stuff. And I highly recommend you to check their projects. So you can just go and look into all their projects and yeah. So and they have some. I showed you that day as well. So they have some very good Pulp XE IPs. Okay. So they have some very nice IPs written in modern system Verilog. So you can, if you want to learn how to build those things, you can just look. I mean, they do like very good work. Okay, so you should like just check them out. But okay, so this Ibex was built part of them their work, and then it became its own thing. Uh, yeah, okay. So and their stuff is stored here. So the idea is like it is a RISC-V core, so it can like basically you can like build what an SoC out of this. So you can put multiple stuff together, like memory, like your accelerators and all this. You can connect them together into an SoC, and it is used in some of the projects, like I think like OpenTitan and like some big projects. They use RISC and this what like Ibex and yeah. So this way, like OpenTitan is it's a root of trust, hardware root of trust, and it's like a hardware security thing, and it's like pretty famous by Google. So they also use this. So yeah. So the thing is like, how can you connect your like accelerator, say something like the systolic array, to any open source RISC-V code or something, right? So we'll give like some what here, like I'll show how I have integrated this, and probably you can get some idea, and then you can do similar stuff as well, right? Okay. So this is our top XE module. So all of this are XE. Okay. So you can to do this integration, what I do is I have cloned this Ibex repo. Okay. And if you dig into that, you can see their simple system. So let me see if you can find it. Examples, simple system. Okay. And here they have like RTL, and then you have the software also, you have simple system, and you have hello test. Okay. Right. So you can see they have a system verilog file for the entire SoC. Okay. So, and you can see this system verilog file if you just like maybe just scan it. It's not like too big. Right. So what they have over here is like the number of devices and number of hosts. Okay. So they have like three devices and one host. So this is sort of like their own terminology on like masters and slaves. So here it means there's one master, that is the CPU, and then you have three different slaves. One of them is a memory, and let's see what are they. So devices are the slaves, right? So and if you scroll down, you can see there's a bus, and this bus connects all the masters to all the slaves. So it is like an interconnect that we discussed on the last week, right? So then if you look at it, there is one module which does the this the top tracing is the CPU, the Ibex CPU with a bunch of wrappers on top of it. And this RAM is like one of the slaves, and then you have simulator control, they have one, and then there's a timer, and there's the another one. So these three are the three different slaves, right? And then they have some like extra stuff. But this is the idea. So now the what you can do is like, now we are going to put our own stuff in here, right? So if you're putting our own stuff, now our thing has like 4 master ports and 1 slave port, right? Like a slave port for the configuration, 4 master ports that talk to the memory, right? So I'm going to use this memory, the memory that they already have here, but I'm going to increase this depth, the size of the memory, so we can put like matrices and stuff. And then what? Yeah. So like our module, like the historic array is like the core part of it, and then we have put like an XE DMAs and everything around, and the DMAs are masters, so they talk to the memory and get the data from the memory, right? So now they should be able to talk to this part and get the data from them, right? So now one way you can do it is you can create this what here you can have what is that um, so that way you can, yeah, over here the number of masters and number of slaves, so you can increase this hosts by 4 if you want, so there's like 5 hosts because now you have 4 DMAs, and now the number of devices you can increase by 1 because you have 1 slave port, right? And by 4, and you can do it that way as well. But then the way I thought is like the system here is very simple. So when I was trying to integrate this, I had like a bunch of issues. So, and then I looked into this bus protocol, what they have, and the actual bus module they have. So this is like a very simple bus. So it doesn't handle like a lot of cases and everything, right? So I didn't want to sort of like put multiple masters, which like what asynchronously keep talking back and forth. And like, I mean, the bus can't handle all that collisions and everything. So what I did was I did something like this. That is okay. So I didn't want to put too much pressure on that Ibex bus. This is the Ibex bus that I'm showing you there. And as I showed, like there are 3 devices on the Ibex side, and you have this one like host on the Ibex side, right? So I didn't want to put too much pressure here. So what I did was basically I used this XC interconnect. Another thing is I wanted to play with the interconnect as well. So the what the Alex Funky is interconnect. So I use this, and then I put so this interconnect has um, 4 slave ports, and I connect these master ports to them. So that way, like now, and on the other side, it exposes 1 master port. So you can combine these all 4 master ports into 1 master port through this interconnect, right? So that's what I did, and that way you're only giving 1 port to this. So you will have like the degradation in performance anyway, right? So because like you have multiple masters talking to the same slave, so you're always going to have this problem. And the Ibex, the simple system and the memory and all are built to not for very performant applications. So I didn't worry about that too much, right? So, and even if you give 4 of this here, this Ibex bus is going to actually combine all 4 into 1 to talk to this memory through a small port, like 32-bit port. So again, like you're going to take the performance hit either here or you're going to get it here. So I might as well do it on my side, right? So that's what that was the reasoning for doing that. Okay. So and after putting all this, so that is the this big module that says the top axis int b. Okay. So let me show you that module. This one, right? So the top axis int v, this one has okay. So this one has what it is a copy of the top axis one. So I have all the DMAs and like all of them, and then I have the crossbar, all of the like all these things, and then I'm using a crossbar to put all these what the axis ports together, right? So this axis crossbar is the module from Alex Frankic, which is the internet, right? So I'm saying like I want 4 slaves here and 1 master here, and I set all these parameters in there, okay? And this is how the crossbar is designed to work. So basically you concatenate all your signals together, okay, into one big array. and you give it the crossbar, and the crossbar will take that and it will work with that. Okay, right. So and yeah, DMA write and DMA write and all. Okay. So okay, I'm using some skid buffers over here to break some paths, and yeah. So there is something interesting. So here that you might it might be okay. So one of the problems I encountered when putting this together was that this design kept hanging, right, for a while. So that's what always happens when you put stuff together, right? So they will just hang, and you won't the thing won't finish, right? It's a common SoC problem, and finding why that happens is will be a bit of a pain, right? So and then you walk through the waveforms and everything, and then okay. So what I found here, the reason for the hang. Okay, so the way this systolic array works, it's like you can see that you are reading stuff from the memory to through here, right? So this you are reading your weights, and then you are reading your say your input and this all this, and similarly you are reading this one as well. So from the memory you are reading that, and you are reading this, and you are reading these partial sums, and then all this, and then you are taking the data and putting it back in here, right? So okay, so what the issue I found at the end, the actual problem was that this DMA is sort of like too greedy. Okay, so what do you mean by greedy? So as I told you before, there's a big advantage of using this open source DMA, that is the performance compared to the Xilinx DMA. And one of the key factors about performance is that when it has this configuration port, right? And the configuration port is an XC light port. So you take and you can um, yeah, so XC light port, and you give your configuration there, and the DMA starts fetching data, and before even it fetches the next data, it takes the next configuration, right? So that way it's very performant. And similarly, on this side, MXC side, so what was going on is that now in the XC protocol, so I think I mentioned it last when I talked about XC last week, that is in the full XC protocol, you can issue requests. So you keep issuing requests, multiple requests, and you don't have to wait for the responses to come before you issue the next request. So you can have multiple outstanding transactions, right? So, and what this DMA does, so I found is that it keeps issuing multiple read transactions to the memory, right? So multiple transactions to the read transaction to the memory. And then what happens is the memory keeps responding here with the data little by little. And then it takes the data and gives to the over here, and it becomes X stream over here. And we saw previously that when this X stream goes in, we have to synchronize with this X stream, right? Because they both have to go in the same time, right? So now this stream also have to come before this one goes in, right? So for that to happen, now this DMA should also get a chance to request something from the memory, right? So, and if that doesn't happen, if this DMA doesn't get a chance to talk to the memory, then this X stream will not be there. This stream will not be there, and only this stream will be there, and this pipeline will be blocked, right? And that is fine. The back pressure builds up, and that is completely fine, right? And then this DMA should stop asking. And when this DMA stops asking, then this DMA can ask. And now the new data comes in, and both data will get together and go inside, right? That is what it should ideally happen, right? But then what I found through going through the waveforms is that in this DMA, the first DMA, it kept giving outputs through, okay, so this side got blocked completely. So this DMA could not send data into it. But then this DMA was actually sending more and more requests on this side. Okay. So the DMA was being sort of like too optimistic. So it is like, I mean, it was thinking, okay, this side might clear up in the future, but I might as well give some bunch of requests, and when the data comes, I can give the stuff, right? So that is what, like, I mean, the like, so the when they as far as when he designed the DMA, he has put the logic that way, right? But then what I found is, like, I mean, now there is a problem. That is, now the DMA is not now it has a lot of outstanding transactions. So now on this side, what happens is that the SXC takes the data, and it takes the data and gives it back through the read data port, right? So like through the data port. And now the DMA can't accept the data because now on this side the stream is blocked. So the data DMA can't accept the data, right? But then if it cannot accept the data, now the what this bus controller, and as well as over here, it's sort of like deadlocked because they are waiting for this DMA to accept this data. But then this DMA cannot accept the data because like this line is not clearing, and this is not clearing because the next one is not ready, and the next one is not ready because, like, I mean, this part is blocked. So this is like a very circular situation, right? So now everybody is waiting for everybody, right? So this is called a gridlock. So like, I mean, it's called a deadlock, right? So deadlock. So it's a very like a I mean, it happens for different reasons, but it's like a usual problem when you are putting XA stuff, or like, I mean, system on chip stuff together, right? So every, like, I mean, you have multiple modules working asynchronously, and like at sometimes like you might have this situation where everyone starts waiting for everyone, and like, I mean, then you can't move the data through it, right? So, and I found, like, I mean, it is the problem is not there in, like, I mean, the access protocol, or it's not there in the design assumptions, stuff like that. Okay. So this arises due to like a specific nature of this problem where like you need to synchronize two things to go in, and both of them are taking data from the memory, and these DMAs are being too greedy, right? So when all these things come together and you have a deadlock, right? So yeah, so I found this problem, and then like, how do you solve this? So one way to solve it is you can probably go into the open source code of this DMA and change it. Okay. But I didn't want to do that because then you have to completely understand the open source code, because every change you make will have like some other problems. It might cause like new bugs, right? So I didn't want that to happen as well. So then at the end, how I solved it is basically like this. That is, I took this signal from here, right? So on this side, we know whether this line is blocked or not from the ready signal. Yeah. So the ready signal that comes from here. Okay. So you use that ready signal to mask the request bus here. So you have a request bus that is AR, address read, right? So you take this AR as access stream bus, and you can mask this mask. So what does it mask means? Mask means you take this valid ready signal and you AND it with the valid that goes here, and the ready that comes back from there. Okay, so that way, like whenever this ready goes down on here, like this DMA thinks that interconnect is not sending data. Okay, interconnect is not giving any not giving any. So basically, this line goes like this. So what you get back from here, there is like the ready. Right? So the interconnect is not giving a ready, and interconnect thinks that this DMA is not giving a valid. So that way, like both of them are not transferring data between each other, right? So the idea is like whenever this goes down, you don't give any more requests. Okay, and then you put like a skid buffer here to absorb some of the data in the middle. So, and by doing that, you can sort of like solve this deadlock problem. So after that, like now, whenever this ready goes down, now the DMA can't give new requests. So when you can't give new requests, now the other DMA gets a chance to give request. So now this DMA gives request and gets data from the memory, and that data goes in with this, and these two go together into the systolic array. Okay, and then like the data just keeps flowing, right? Okay. So any questions about this? All right, there is a question. When I went through the open source Axie repo, I found Axie interconnect cannot have concurrent read-write transactions. Is that the reason you use Axie crossbar instead of Axie interconnect? Um, okay, so the Axie interconnect cannot have concurrent read-write transactions. So that is one of the reasons. So like usually, I think the interconnect is a less performant than a crossbar. So that is one of the reasons. And the other one is like I wanted to like sort of but experiment with the crossbar and see like I mean how it works, whether it has any problems. So can I add new modules into that, or like in a sense, can I, because I have not used the open source crossbar, so I've used like the ZYNQ crossbar all this time. So then I was thinking like I mean, oh, I want to see like how that works and all that. So and crossbar is like a little more complicated module than Defect, so that's why I used it. But I mean, in your case, if you don't want to have like concurrent read and write, then you can use like the Axie interconnect as well. Okay, that's a good question. Yeah. All right. So yeah, now let's move on to how this integration sort of works. And okay, is live lock is another similar situation to deadlock. So personally, I haven't actually encountered live lock. Uh, so let me quickly check the. Yeah, I'm not sure like about how the live lock happens in SoCs. Like I have only but I have had like deadlock problems. So live locks are more like a this thing. What is that? Um, the concurrency thing. I think that is like with threads and like all that. So I'm not sure like whether they apply to SoCs as well. So this deadlock is like much less of a problem in SoCs in the sense like we do still have this problem that like I mean as it is told it will happen once in a while, but there are this another complete class of SoCs called the NOCs, NOCs, right? So these NOCs usually have like an array of stuff and they sort of dynamically talk to each other and dynamically route the data from one to another and like all that. So this deadlock is sort of like a big problem in NOCs, and there are like very many ways algorithms to handle and like avoid this deadlock issues in a knock and stuff like that. But then I mean in our kind of SoC situation there is not like a what what it doesn't have like I mean that much study or like in the sense it's not like its own area to avoiding deadlock. Okay, all right, so let's see how we put this together. So top scene, so you can see the way I have done this. So there's this skip buffer, and then you have the mask. Yeah, so you can see I have masked the signal. Okay, and I have used the axis stream signals ready signal, and I have masked this AR valid and AR ready. So these are the request signals. Okay, so I have masked these two by doing this, like I'm like trying to stop the DMA from being too greedy, right? Like asking requests when it can't accept data. Okay, okay. And then on this side, we have, okay, let's see how this thing is put together. So you have top axis int. And if you look at the top SA for Ibex, okay, yeah. So you have, okay. So now to do this, now I have this, yeah. So I'm using this X axis to host module. Okay. So this is a more like a simple module that converts the axis protocol into this the host and LSU protocol. So you have, let's see. Ibex LSU load store. Yeah, this thing. Yeah. So this is the protocol from Ibex to load and store stuff. So, and this is a much simpler protocol than XC, right? And yeah, you have address and this and like basically what and it's a little more straightforward. But the thing is like we need to convert our XC module into this. Okay. So if our XC protocol into this. So this is like a what module that does that conversion. And similarly, you have dev to MSL. Okay. So this is the one that connects the device port. So that is the Ibex slave port to like our what okay. So this one basically connects, I think yeah. So it connects the Accelerate master to the Ibex device side, right? So and here the idea is like sort of this is how the on this side you have the memory from Ibex, and on this side we have the actual the Axie masters, and all of them put together into one the Axie interconnect. Okay, and I think I'm using this. All right, okay. So the host and is defined with respect to the bus. Okay, so this is our module. Okay, so top Axie int. And this one has the one Axie light port, so which does the what configuration, and there's a slave port, and then you have one big master port which does all this, what which like comes from the interconnect, right? And this master port is connected to our um, S-axis to host, and on the other side you get the these host signals. Okay, so these host signals, you get one host, like basically one set of host signals. And similarly, the all these XC light port, like you connect them to the dev signals, right? And in the top module of the IPX simple system, okay, so this is the top module. And in the top module, you can see in the bus, I have connected that into over here. Yeah, let's say for IBEX. Okay, so you have a device and then you have a host. Okay, so yeah, so and this one directly goes into the IBEX bus, and then this one also goes into the IBEX bus, and that is how it talks to the memory. Okay, so and there are like a couple of things over here that is yeah. So we looked at the firmware yesterday, how we start and stop stuff. And if you look at the C code for IBEX, okay, so this is the C code for IBEX. And in here, like I am first just writing and reading from this what config registers. So this is when you are putting your own module, okay. When you are putting your own module inside, then like it is um so one of the first steps, or one of the first things that goes wrong, like I mean, so as you know, right, like as engineering students, when you put like a big thing together, like I mean, the first time it doesn't work at all. So it takes like 10, 15 times to get things working. So, and the first thing that usually goes wrong or that you have to debug is the path to reading and writing to registers. Okay, whether that path is working. Okay, so the first part that actually does this, so over here, so I'm writing to a particular config base address. Okay, so the like this is the config base address. From that address, I'm like implementing something, and to that address, I'm writing some stuff, and I'm reading it back. Okay, so and like if you are putting it together for the first time, this part will not work. You have to see why it doesn't work and all, and you have to fix it, right? And you can see it on the waveform, like where things are going wrong. Okay, And once this goes in and you can read it back again correctly, then you have what you can go and do the next part. So I'm randomizing the bunch of inputs, and I'm run function is this one, and then I'm checking the outputs. Okay. So here's something that is interesting over here is that like now this one, the Ibex doesn't have any this stuff like printf and everything, right? It doesn't have the standard library, C standard library. Okay. So why? Because it's a small RISC-V microcontroller. So it doesn't support these things. So then, so like this is a very simple, like a function which emulates the printf. Okay. I mean printf and yeah. So, okay. So if you're interested in the C level stuff, then you can like probably take a look into this as well. So this is like a very simple case of printf. So C has this interesting feature of like having variable number of arguments in function, right? So and this is how it is actually implemented. Okay. So and I think that feature was introduced in C back in the day, like by 80s or 90s or something, to support printf itself, because like you need to have a multiple what you need to have like a unlimited number of arguments for that, right? So yeah, basically like I mean, so this is how like these things are put together, and so yeah, I have that. So and let me see. So you go into this like make enter into that and do a make Ibex test. Okay, and when you enter, like it will do this. Okay, so it is building all these things, and then but it has its own build system called FuseSock. Okay, so that might be interesting for you to like probably can look into it, like how that works and all. So I have created some stuff for that. So that is like to connect our design to FuseSock, you need to have this FuseSock is a build system, right? Basically that puts all the SoC stuff together, right? So and like basically have a file list and like I mean give it to different tools. So FuseSock does that, and the way you can do that is like this. So there is file set, and you can have to mention all your files, okay, that you're going to use, and then you have like what is your top like I mean RTLV files and stuff like that. Okay, right. So and when you do this make enter and you write make Ibex test, it is going to run FuseSock and it will build all these modules, right? So and it will compile all the modules and everything, and then it starts very later, right? So and when it runs very later, you can see what like yeah. So you can see like the performance counters and everything, and here you can see I'm printing this log from that comes from the what is it from the terminal. So all that std in, std out, right? And so it shows like prints the address I asked for here. Okay, so this address. So it only has puts and put X and all that. So like very simple stuff. And yeah, it basically prints the address, the value, and then like it runs the whole code and it says like all output match, right? So I'm sort of running it again, I guess. Yeah. Okay. So you can do this yourself. Okay, make IDEC test, and you can see how this thing, the whole thing runs. And if you open this wave, okay, GTK wave sim FSD, I'm not sure if you can open from this terminal. Let me see. Yeah, I think it's probably because I can't get the GUI out of this one. Okay. Any questions in this integration? Okay, yeah, you can just do make wave. So I have automated that part as well. Um, and if you look into that, so okay, so I think to make iWave. So that is the Ibex waveform. So you can see the whole sort of design here. Okay, simple system. So you can actually see the all the signals even inside the CPU and everything. So that is the like the beauty of open source stuff, right? And then you can systolic array, U bus. Okay, you can see the data moving and okay. All right. So yeah, I think that is it with the IBEX integration and all. So okay. So if you have any questions and everything, like you can ask me. So we'll have like 5 minutes and like yeah, if there are no questions, we can end it. Yeah. So will you plan to initiate a new course related to SoC design based on this workshop in the future? So I am thinking of that, but then the thing is like I don't feel like there is enough content for that. So especially like from like this sort of perspective. So I mean the whole point of this particular workshop was to give I mean so to sort of boost the students like who already are building accelerators. So like if you want to build accelerators to get them running quickly. So I think that is very valuable for students, like I mean, to for publishing and then like I mean, doing GitHub projects and stuff as well, right? So I think like it's much cooler to like go more interesting to build stuff than to like fight with all this. And on a general SoC stuff, I mean, I'm not sure like if there's enough content right now with me to do this. So later on, like if I when I learn more and like I mean when I have more material, like we'll probably build a course around it. So that's what I'm thinking. Yeah, but like that's probably like maybe a year or something later. Yeah, yeah. And the other thing is like I mean if you guys are interested in what SoC stuff, then you can check out some of my SoC projects and you can do something similar. Okay. So the one of the this is our like undergrad stuff. They probably actually have the same thing again. So that is we built this system bus and we built a custom protocol and but we also built like an external protocol and an arbiter. We built master slaves and everything. So it was like a very interesting thing. And I sort of learned what how not to build a bus like in this course. Okay, so and I think that is very important to learn in the sense like why are things the same way and some way and why are not some other way. So and then like you can look at say so this is the access stream verification IPs, right? So Okay. And then, yeah. So this is about Firebridge. So you might have seen the FB underscore stuff, right? Like in this code, that the stuff I'm using it to talk between system verilog and C in during simulation and everything. So if you want to learn a little more about that, and like I mean, you can use it as it is. That's not a problem. So and if you want to know how it works, I mean, you can look at the code also. It's not that hard. But then if you want some information, you can look at it here. So that is one of the projects. And yeah, and this is the systolic array testbed part. Okay. Yeah. So one of the more interesting things I'm doing with this, you may not be able to replicate it because you may not have the tools for that. Is that formal verification, right? So I'm trying to formally verify this systolic array, and you can look at my attempts on like over here inside this formal. Okay. So it is in this tbsa.sv. Okay. So, and I'm using a like an interesting method called like a formal, like it's called a ghost abstraction. So the idea is you like in formal verification, you don't write the signals manually like normal verification one by one. So what you do is you just put a signal up here without driving it. And let me see where it is. Oh yeah, this one's XMAT and KMAT and all that. So, and you don't drive them at all. So when you don't drive them, the formal verification tool will understand now this should be considered as any for any value, right? And the tool will try to prove it such that like for any X matrix and K matrix and everything, this systolic array does matrix multiplication, right? And then like similarly, it also does all the like axis stream like stuff, and you can look at it. So that is, I think, like a very interesting stuff. It's like more mathematical and like, but then I think like you need some actual what some proprietary tools to do this. The open source tools were not very good at it, like in the sense it was very hard to work with them. So, but yeah, if you have any open source stuff, you can try that as well. Okay, and yeah, lightweight, formal. So I have some formal stuff here. You can look at it, and yeah. Okay. So yeah, there's a question. Maybe later, can you add something related to hardware security? Yeah. So that is an interesting topic. I'm learning a bit about hardware security these days as well, for my PhD. And so this is like one thing I'm building, like a hardware fuzzing framework. Okay. So you can probably take a look at it, and you can see how it works and all. So but this one is like a private repo, so you won't be able to look at the code and everything. Yeah. So there are like different aspects to it, and so I'm more interested in like actually how we can make actually secure or things like that. Okay. So there are like, I mean, even that you can do it in like many different ways. So yeah, probably in the future we can probably have a seminar where we discuss hardware security stuff. But yeah, like it's like more of a niche field and like only like a few people like study that. Okay. Any questions?
Thank you for the amazing webinar. And I have one question that I was trying to design a AI accelerator by using this systolic array. And
Mhm.
for that, is it sufficient? Do I need? Is it sufficient to design that? I was trying to design it by using Vivado environment because that is what I was familiar. So, is it sufficient to design a Vivado environment and finally design the block diagram and generate the bit stream and deploy into the FPGA? Or should I go for the Ibex integration? Uh, is it sufficient to design kind of AI accelerator and end the workflow right after the deployment to the FPGA by using Vivado environment? Or should I go for
Mhm.
the Ibex integration?
So it sort of depends on your goals. So I think like I mean Ibex is so like they're like two different things. So one is when you put it on FPGA, you can actually see it working in real world. So I think like that is very cool. And then like sort of like if you are publishing and everything, again like you have the FPGA conference and AC conferences are sort of different, right? And I don't think like a lot of ASIC conferences care too much about the SoC integration or like stuff working end to end or anything. So they are mostly like you have this accelerator and you try to do like I mean say do synthesis and like try all that, right? So um in that case, I think like I mean the reason I used Ibex is because like I want to do something similar for a different project. So I have an accelerator called CGRFML up here. So I'm trying to get that thing running like with and I got it running with Ibex, right? Like by doing this. So but then and later on like because my one of my friends over here who is doing PhD with me is building a simulator. So like he wanted some like an entire SoC that can be simulated. So that's why I did the Ibex stuff. But in your case, I would recommend you to like, I mean, first of all, do the like Vivado thing, okay? And one more interesting thing that you can do is actually like if you have an AI accelerator, you can interface it to Linux. So that part I haven't done it yet here. I have a few undergrads who are working on that. So and probably in a few months we will have that ready. So the idea is sort of like now we have the C firmware which runs on bare metal, right? So when you say bare metal, it means it runs on this like ZYNQ FPGA, and that is like raw without any operating system, right? So, but like the next step is like, can you do it with some what is it? Yeah. So the next step is like, can you do it with Linux, right? So you have Linux running in the ARM processor, and then like it talking to and back and forth from here. So I think that is a little more valuable because like then you can send data through Ethernet or something, and Linux can handle all of that. And then you can boot Linux, and then you can use the accelerator as some sort of like another GPU or something, right? Which is very cool, right? So if you're doing something like on the FPGA, I recommend you to do that. And if you are reporting numbers or something, then like doing it from the Linux level is like way more interesting, right? But then like you also have to remember, like, I mean, once you go to like from RTL level to SoC level to Linux level, your performance, the actual performance measured is going to go down, 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 right? So because you have little more movement of overheads. So I mean, and you can, if you are publishing, then you can publish, okay, like on RTL level, we are getting this much. On bare metal, we are getting this much. Linux, we are getting that much. So that we can do that, right? And that will be very, like very interesting. And I think like having this full integration will help you to find jobs, will help you to find like internships and all of that. So yeah, I recommend you to do that. But yeah, so the Ibex or any other open source stuff is valuable only if you want to sort of like put like like entire SoC, open source SoC, and then maybe you want to generate a GDS or something, you want to take it through ASIC flow, you can do that. Okay. Oh, so you can do stuff like that, right?
Okay, thank you, sir.
All right. Any other questions? All right. Okay. Thank you so much. Yeah. So you can reach out to us through like the SkillServe platforms, or like I mean through the emails and everything. And if you have any questions, and we can answer. And if you have any future projects, we can tell you as well. Okay. Thank you. Thank you for attending.